Picture this: the universe is flying apart faster and faster every second, and nobody knows why. Galaxies are racing away from each other like cosmic shrapnel from an explosion that happened 14 billion years ago. But here's the terrifying part. Something invisible, something that makes up 70% of everything that exists, is pushing the accelerator harder. Scientists call it dark energy, and it might be the most important mystery in all of physics, because understanding what's driving our universe apart isn't just about satisfying curiosity, it's about discovering whether the cosmos will end in ice, fire, or something stranger than we can imagine. If you're fascinated by the universe's deepest mysteries and want to explore more mind-blowing cosmic revelations, make sure to subscribe to this channel and hit the thumbs up. Now let's begin. In 1998, two teams of astronomers made a discovery that shattered everything we thought we knew about the universe. The Supernova Cosmology project and the High-Z supernova search team were studying distant stellar explosions called Type Ia supernovae. These cosmic lighthouses shine with predictable brightness, making them perfect for measuring vast distances across space. The teams expected to find the universe's expansion slowing down, pulled back by gravity like a ball thrown into the air. Instead, they found something that made physicists question reality itself. The universe wasn't slowing down, it was speeding up. Imagine standing at the edge of a cliff and dropping a stone only to watch it fall upward, accelerating into the sky. That's essentially what these astronomers discovered on a cosmic scale. Galaxies aren't just moving apart, they're moving apart faster and faster, driven by an invisible force that defies everything we understand about physics. This discovery was so revolutionary, so paradigm-shattering, that it earned the 2011 Nobel Prize in Physics. But let me take you deeper into what this really means. When we look at distant galaxies, we're seeing them as they were billions of years ago because light takes time to reach us. The Hubble Space Telescope and now the James Webb Space Telescope act as time machines, showing us the universe's history written in light. What these observations reveal is mind-bending. About 5 billion years ago, something fundamental changed. The universe shifted gears from slowing expansion to acceleration, like a cosmic driver suddenly flooring the gas pedal. The evidence comes from redshift, the stretching of light waves as objects move away from us. It's the same principle that makes an ambulance siren drop in pitch as it races away. But with galaxies, we're talking about light waves stretching across billions of years of travel. The more distant the galaxy, the more its light has stretched, telling us how fast it was receding when the light began its journey. Type Ia supernovae in these distant galaxies appear dimmer than they should be if the universe were expanding at a constant rate. They're farther away than expected, revealing acceleration. Recent data from the Dark Energy Survey, which photographed hundreds of millions of galaxies across 1/8 of the sky, confirms this cosmic acceleration with unprecedented precision. Using the Blanco telescope in Chile, scientists created the most detailed map ever of how matter clusters in the universe. What they found reinforces the terrifying truth. Dark energy dominates our cosmos, making up about 70% of everything that exists. Think about that for a moment. Everything you see, every star, planet, galaxy, every atom in your body represents less than 5% of the universe. Dark matter, that invisible scaffolding that holds galaxies together, makes up another 25%. But dark energy, this force pushing everything apart, dominates everything else. We live in a universe where the visible is a tiny minority, and the majority is an invisible force working against gravity's pull. Speaking of gravity, have you ever wondered if gravity can travel faster than light? I have covered that in my video called "Does Gravity Really Travel Faster Than the Speed of Light?" If you're fascinated by gravity, relativity, gravitational waves, and the universe's deepest mysteries, this video is a must-watch. Check it out after this video. The link is in the description and pinned on the comments. Now let's continue. The Planck satellite, launched by the European Space Agency, mapped the cosmic microwave background, the afterglow of the Big Bang, with extraordinary precision. This baby picture of the universe, taken when it was only 380,000 years old, contains subtle patterns that reveal dark energy's presence even in the early cosmos. The way matter clumped together back then, the size of hot and cold spots in this ancient light, all point to dark energy's influence stretching back billions of years. But what exactly is dark energy? Here's where our story becomes even stranger. The leading explanation involves something Einstein called his greatest blunder, the cosmological constant. In 1917, Einstein added this constant to his equations of general relativity to keep the universe static, neither expanding nor contracting. When Edwin Hubble discovered cosmic expansion in 1929, Einstein abandoned the constant, calling it his biggest mistake. But dark energy's discovery resurrected this blunder in a new form. The cosmological constant represents the energy of empty space itself. Quantum mechanics tells us that even perfect vacuum seethes with activity, virtual particles popping into existence and annihilating in time frames too brief to measure. This quantum foam should have energy, and that energy should cause space to expand. It's an elegant explanation with one catastrophic problem. When physicists calculate how much energy the quantum vacuum should have, they get a number that's 10 to the power of 120 times larger than what we observe. This is the worst prediction in the history of physics, a discrepancy so vast it defies comprehension. Imagine predicting that a mouse weighs as much as the observable universe. That's the scale of error we're talking about. This vacuum catastrophe suggests something fundamental is wrong with our understanding of physics at its deepest level. Either quantum mechanics is incomplete, general relativity needs modification, or some unknown mechanism cancels out most of the vacuum energy, leaving just enough to drive cosmic acceleration. Recent observations from the Atacama Cosmology telescope in Chile have measured the cosmic microwave background's polarization, revealing how dark energy affected the universe's earliest moments. These measurements show that dark energy's influence has remained remarkably constant over cosmic time, fitting the cosmological constant model. But this constancy itself is puzzling. Why should empty space have exactly this amount of energy, not more or less? The Dark Energy Spectroscopic Instrument, or DESI, currently conducting the most ambitious survey of the universe ever attempted, is creating a three-dimensional map of 35 million galaxies. Early results suggest dark energy might not be perfectly constant after all. There are hints, tantalizing but not yet conclusive, that dark energy's strength might vary slightly over cosmic time. If confirmed, this would revolutionize physics, suggesting dark energy isn't a property of space itself, but something dynamic, perhaps a new field permeating the universe. Let's explore one of the most mind-bending possibilities. Dark energy might not be energy at all. Some physicists propose that what we interpret as cosmic acceleration could be our first glimpse of extra dimensions. String theory, our best attempt at unifying quantum mechanics and gravity, requires additional spatial dimensions beyond the three we experience. These dimensions might be tiny, curled up smaller than atoms, or vast, with our universe floating like a membrane in higher dimensional space. The Large Hadron Collider at CERN has searched for signs of extra dimensions by looking for missing energy in particle collisions, energy that might escape into dimensions we can't see. While no smoking gun has emerged, the possibility remains tantalizing. If gravity can leak into extra dimensions while other forces remain confined to our three-dimensional space, it could explain both gravity's weakness and dark energy's effects. What we see as acceleration might be gravity diluting into higher dimensions over cosmic distances. Recent gravitational wave detections by LIGO and Virgo have opened an entirely new window for studying dark energy. When black holes merge, they send ripples through space-time that travel at light speed across the universe. By comparing how these waves stretch during their journey with how light from the same events redshifts, scientists can measure cosmic expansion with unprecedented precision. The neutron star merger detected in 2017, which produced both gravitational waves and light, provided our first standard siren, a new cosmic ruler for measuring dark energy's effects. But here's where things get truly strange. Some theories suggest dark energy might be a sign that our universe is approaching a phase transition, like water about to boil. The Higgs field, which gives particles mass, might not be in its lowest energy state. If it transitions to a lower state, bubbles of new physics could form and expand at light speed, rewriting the laws of nature as they go. Dark energy might be the pressure building before this cosmic phase change, a warning that our universe's current form is temporary. The Euclid Space Telescope, launched by the European Space Agency in 2023, is conducting an unprecedented survey of billions of galaxies to map dark energy's influence across cosmic history. Its early observations are revealing the cosmic web's structure in extraordinary detail, vast filaments of dark matter decorated with galaxies like lights on cosmic strings. The way these structures have grown over billions of years provides crucial clues about dark energy's nature. Consider this profound possibility. Dark energy might be connected to information itself. The holographic principle suggests that all information in a volume of space can be encoded on its boundary, like a hologram storing three-dimensional information on a two-dimensional surface. If our universe is fundamentally holographic, dark energy might represent the computational cost of processing reality. As the universe expands and complexity grows, more computational resources are needed, manifesting as the acceleration we observe. Recent studies of black hole thermodynamics support this information-based view of physics. Black holes have entropy proportional to their surface area, not volume, suggesting information is fundamentally two-dimensional. The universe's accelerating expansion might be driven by the ever-increasing information content of cosmic evolution. Every quantum interaction, every moment of consciousness, every new pattern adding to the computational load that manifests as dark energy. The South Pole Telescope has detected subtle distortions in the cosmic microwave background, caused by dark energy's influence on light's journey across billions of years. This integrated Sachs-Wolf effect occurs when photons gain energy falling into gravitational wells that are stretching due to cosmic acceleration. It's like surfing cosmic waves that grow while you ride them, providing independent confirmation of dark energy's reality. Let me share something that reveals just how precisely balanced our universe is. If dark energy were just slightly stronger, cosmic acceleration would have begun earlier, preventing galaxies from forming. Stars would never have ignited, heavy elements would never have been forged, and life would be impossible. If dark energy was slightly weaker, the universe might have already begun contracting, crushing everything in a big crunch. We exist in a narrow window where dark energy is strong enough to drive acceleration, but weak enough to allow structure formation. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct the most detailed dark energy survey ever attempted. By observing millions of Type Ia supernovae and mapping dark matter through gravitational lensing, it will trace cosmic acceleration's history with unprecedented precision. These observations might reveal whether dark energy is truly constant or evolves over time, potentially unlocking its nature. But what if we're thinking about dark energy entirely wrong? Modified gravity theories propose that Einstein's general relativity breaks down on cosmic scales. Just as Newton's gravity required Einstein's corrections for extreme conditions, perhaps Einstein's theory needs modification for the universe's largest structures. Modified Newtonian dynamics, and its relativistic extensions suggest gravity behaves differently when accelerations are extremely small, potentially explaining cosmic acceleration without invoking dark energy. The Vera Rubin Observatory, beginning its legacy survey of space and time, will photograph the entire visible sky every few nights for 10 years. This cosmic movie will reveal how dark energy affects everything from asteroid orbits to distant quasars. By tracking billions of objects over time, scientists will test whether dark energy is uniform across space or varies in ways current theories can't explain. Recent computer simulations of cosmic evolution have revealed something unexpected. Dark energy's dominance might be temporary. In the far future, if dark energy is phantom energy, a form that grows stronger over time, it could tear apart all structures in a Big Rip scenario. Galaxies would dissolve, solar systems would unbind, and eventually even atoms would be torn apart. The universe would end not in ice or fire, but in an ever-accelerating dissolution of everything. The cosmic coincidence problem adds another layer of mystery. We happen to live at the precise cosmic epoch when dark energy and matter have comparable densities. Earlier, matter dominated completely. Later, dark energy will dominate overwhelmingly. Why do we exist at this special transition time? This coincidence might hint at deeper connections between dark energy and the conditions necessary for observers like us. Quantum entanglement experiments have revealed that information can be shared between particles instantaneously, regardless of distance. Some theorists wonder if dark energy might involve similar non-local effects on cosmic scales. Perhaps the universe's acceleration reflects quantum correlations between distant regions of space, a cosmic entanglement driving expansion through mechanisms we don't yet understand. The multiverse hypothesis offers another perspective on dark energy. If our universe is one of countless bubbles in an eternal inflation scenario, each with different physical constants, then dark energy's value might vary between universes. We find ourselves in a universe with this particular dark energy value simply because other values don't allow observers. It's an anthropic explanation that some find unsatisfying, but others see as inevitable given cosmic inflation's implications. The most recent data from the James Webb Space Telescope has thrown another wrench into our understanding of dark energy. JWST has discovered massive, mature galaxies existing just a few 100 million years after the Big Bang, structures that shouldn't have had time to form if our models of cosmic evolution are correct. This might mean dark energy behaved differently in the early universe, perhaps being weaker or even attractive rather than repulsive, allowing matter to clump together more quickly than we thought possible. Let me paint you a picture of the cosmic web that dark energy is slowly tearing apart. Imagine the universe as a vast foam, with galaxies living on the surfaces of bubbles. The bubbles are cosmic voids, regions where dark energy's repulsion has cleared out matter. Between these voids stretch filaments of dark matter and galaxies, like soap films connecting bubble walls. Dark energy inflates the voids, stretching the filaments thinner and thinner. We're watching the slow-motion dissolution of the largest structures in existence. The Sloan Digital Sky Survey has mapped millions of galaxies, revealing baryon acoustic oscillations, frozen sound waves from the universe's infancy. These cosmic ripples, set in motion when the universe was a hot plasma, provide a standard ruler stretching across billions of light years. By measuring how this ruler appears stretched at different cosmic epochs, astronomers track dark energy's influence through time. It's like watching the universe breathe, with dark energy controlling the rhythm of expansion. Here's a possibility that keeps cosmologists awake at night. Dark energy might be a fossil field from cosmic inflation. In the first fraction of a second after the Big Bang, the universe expanded faster than light, driven by an inflation field that eventually decayed. But what if it didn't decay completely? Residual inflation energy, frozen into the fabric of space, could manifest as the dark energy we observe today. We might be seeing echoes of the universe's violent birth, still shaping its future. Recent observations of cosmic voids, those empty regions between galaxy clusters, reveal they're not truly empty. The Dark Energy Survey found that voids contain faint galaxies and dark matter halos, but at much lower densities than elsewhere. These cosmic deserts are dark energy's domain, regions where repulsion dominates attraction. Studying how voids grow and merge provides unique insights into dark energy's properties, like watching bubbles expand in cosmic champagne. The Hubble tension, a discrepancy in measurements of the universe's expansion rate, might be our first clue that dark energy isn't what we think. Measurements using the cosmic microwave background suggest one expansion rate, while observations of nearby supernovae indicate a rate about 9% faster. This difference is too large to be an experimental error. It might mean dark energy has evolved over cosmic time, or that new physics operates between the early and late universe. Consider the vacuum metastability disaster scenario. Quantum field theory suggests our universe's vacuum might be metastable, stable for now, but capable of transitioning to a lower energy state. If this transition began anywhere, it would spread at light speed, destroying everything. Dark energy might be related to this precarious balance. The universe's acceleration could be a symptom of vacuum instability, like cracks spreading through cosmic ice before it shatters completely. The Eurositer X-ray telescope has detected hot gas in galaxy clusters across half the sky, revealing how dark energy affects the universe's largest gravitationally bound structures. As cosmic acceleration pulls clusters apart, their hot gas cools and disperses. By measuring gas temperature and density in clusters at different distances, scientists trace dark energy's impact on cosmic structure formation. It's like taking the universe's temperature to diagnose its dark energy fever. Let's explore the chameleon field theory, where dark energy's strength depends on local matter density. In this model, dark energy is weaker near massive objects and stronger in empty space. This environmental dependence could explain why we don't see dark energy effects in our solar system, while they dominate on cosmic scales. Laboratory experiments using atom interferometry and torsion balances search for chameleon fields, trying to detect dark energy in Earth-based experiments. The cosmic neutrino background, relic neutrinos from the Big Bang's first second, might hold clues about dark energy. These ghostly particles, which outnumber atoms by billions to one, have such low energy they've never been directly detected, but their collective gravity affects cosmic structure formation. If neutrinos have certain mass patterns, they could interact with dark energy in ways that explain cosmic acceleration. The Katrin experiment in Germany and other neutrino observatories are closing in on neutrino masses that might unlock this connection. Recent analysis of the Lyman alpha forest, absorption lines in quasar light from intergalactic hydrogen, reveals how dark energy affects matter on intermediate scales. As light from distant quasars passes through billions of years of cosmic evolution, it picks up signatures of every gas cloud along the way. The pattern of these absorption lines traces cosmic structure growth, showing how dark energy has gradually overcome gravity's pull throughout cosmic history. The possibility of interacting dark energy opens fascinating scenarios. Instead of being completely separate, dark energy and dark matter might interact through forces beyond gravity. This coupling could explain several cosmic puzzles, including why dark energy dominates now rather than earlier or later. Observations of colliding galaxy clusters, where dark matter and normal matter separate, provide laboratories for testing these interactions. Primordial black holes formed in the universe's first moments offer another dark energy connection. If these ancient black holes exist in sufficient numbers, their evaporation through Hawking radiation could contribute to dark energy. As black holes slowly dissolve, they might inject energy into space itself. This mechanism would link dark energy to quantum gravity, potentially solving multiple mysteries simultaneously. The anthropic principle becomes unavoidable when discussing dark energy. The observed value is suspiciously close to the maximum that still allows galaxy formation. Slightly more dark energy and cosmic acceleration would have prevented matter from clumping into stars and galaxies. This fine-tuning might indicate a multiverse where different regions have different dark energy values, with observers necessarily finding themselves in hospitable regions. Gravitational lensing tomography, using the distortion of distant galaxy images to map intervening matter, provides a three-dimensional view of how cosmic structure evolves under dark energy's influence. The Dark Energy Survey and upcoming Legacy Survey of Space and Time will measure shapes of billions of galaxies, creating the most detailed map ever of how dark energy has shaped cosmic architecture over the past 10 billion years. Let's revisit the ultimate fate of the universe, because dark energy completely rewrites the ending. For decades, scientists debated two possibilities: a big freeze, where the universe expands forever until it's a cold, dark, empty place, or a big crunch, where gravity eventually wins, pulling everything back into a final, fiery singularity. But dark energy introduces a third, terrifying possibility: the Big Rip. If dark energy is a phantom energy that grows stronger over time, its repulsive force will eventually overwhelm everything else. In about 20 billion years, the Big Rip would begin. First, the cosmic web would dissolve as galaxy clusters unbind. Then, galaxies themselves would be torn apart. In the final 60 million years, stars and planets would be ripped from their orbits. In the last minutes, Earth would explode. In the final fractions of a second, atoms themselves would be torn asunder, and the fabric of space-time would unravel. It's the most violent end imaginable, a universe torn to shreds by its own accelerating expansion. But not all theories predict such a dramatic end. The leading alternative to Einstein's cosmological constant is a concept called quintessence. Imagine a new energy field that permeates all of space, like a cosmic weather system that can change over time. In this model, dark energy's strength isn't fixed, but evolves as the universe ages. Quintessence could be this field slowly rolling down an energy hill, releasing potential energy that drives cosmic acceleration. The Euclid and Roman space telescopes are designed specifically to test this idea. By measuring cosmic expansion at different points in history with incredible precision, they can determine if dark energy's strength has changed. If they find even a tiny variation, it would be a death blow to the cosmological constant theory and a huge victory for quintessence. It would mean dark energy isn't a property of space itself, but a dynamic, evolving component of the cosmos. This brings us back to the cosmic coincidence problem. Why is dark energy only becoming dominant now? If it's a dynamic field like quintessence, this timing might not be a coincidence at all. Some models suggest quintessence could be linked to the formation of structures like galaxies. Perhaps dark energy was dormant until enough matter had clumped together, triggering a cosmic feedback loop that ignited its repulsive force. We might live at a special time because it's the era when the universe woke up its dark energy. Here's another profound implication. Dark energy affects the universe's ultimate information capacity. The Bekenstein bound, a fundamental limit in physics, states that any region of space has a maximum amount of information it can contain. As dark energy drives galaxies apart faster than light, our cosmic horizon shrinks. We see fewer and fewer galaxies over time. In the distant future, our galaxy will appear as a lonely island in an empty void. This means the observable universe's information content is decreasing. Dark energy is literally erasing parts of the cosmos from our view forever. But does dark energy affect things on a smaller scale? We know with incredible precision that it doesn't. The Cassini spacecraft, which orbited Saturn for over a decade, provided some of the most stringent tests of general relativity ever conducted. By tracking its trajectory with pinpoint accuracy, scientists showed that if dark energy exists within our solar system, its effect is so small it's undetectable. This confirms that whatever dark energy is, it operates only on the largest cosmic scales, a force that shapes the universe but ignores planets, stars, and people. This scale dependence is a crucial clue. It's why modified gravity theories remain so appealing to some physicists. These theories propose that gravity itself changes its behavior over vast distances, creating an illusion of acceleration. It's like looking at a distant object through a warped lens. The object isn't actually moving differently, our view of it is just distorted. The challenge for these theories is to explain all cosmic observations, from the cosmic microwave background to galaxy clustering, without invoking dark energy. So far, none have succeeded as well as the standard dark energy model. Let's consider the thermodynamic implications. The universe's entropy, or disorder, is always increasing. This arrow of time is deeply connected to cosmic expansion. But dark energy introduces a new wrinkle. A universe dominated by a cosmological constant has a specific temperature associated with its cosmic horizon, known as the Gibbons-Hawking temperature. It's incredibly cold, but it means that even in the far future, the universe won't reach absolute zero. It will remain a vast, empty void with a faint, residual warmth, a cosmic hum left over from the energy of space itself. The ultimate goal of physics is to find a theory of quantum gravity, a single framework that unites Einstein's relativity with quantum mechanics. Any successful theory must explain dark energy from first principles. String theory offers possibilities, suggesting dark energy could relate to the vibrations of extra-dimensional membranes. Loop quantum gravity proposes that space is made of discrete quantum loops, and dark energy might be a cumulative effect of these quantum building blocks. But for now, these are just tantalizing ideas, mathematical sketches of a theory we don't yet have. The mystery of dark energy reminds us that we are just beginning our cosmic journey. The discovery that our universe is accelerating, made only a few decades ago, is as profound as humanity's realization that Earth is not the center of the solar system. It forces us to confront our ignorance. 70% of the universe is a complete mystery, a force we can see affecting everything but whose nature remains totally unknown. It's a humbling and exhilarating position to be in, to know that the biggest discoveries still lie ahead. Every new telescope, every new particle accelerator, every gravitational wave detection is a step deeper into this mystery. We are cosmic detectives, gathering clues from ancient light and ripples in space-time to solve a puzzle that spans 14 billion years and determines the ultimate fate of everything. The answer, when we find it, will not just change our textbooks, it will change our place in the cosmos. The latest breakthrough comes from an unexpected source: artificial intelligence. Machine learning algorithms trained on millions of galaxy images are finding patterns humans missed. These AI systems can identify subtle gravitational lensing effects, caused by dark matter and trace how cosmic structures evolved under dark energy's influence. The algorithms have discovered that dark energy's effects might not be perfectly uniform across the sky. There are hints of cosmic anisotropy, regions where acceleration appears slightly stronger or weaker. This potential discovery of cosmic direction would shatter one of cosmology's fundamental assumptions, that the universe looks the same in all directions. If confirmed, it could mean dark energy isn't a smooth, uniform field, but has texture, structure, perhaps even currents and eddies like a cosmic ocean. The implications would revolutionize physics, suggesting our universe might be just one region in a much larger, more complex cosmos where dark energy varies like weather patterns. Let me tell you about the most ambitious experiment ever proposed to study dark energy, the Laser Interferometer Space Antenna, or LISA. Scheduled for launch in the 2030s, LISA will be a gravitational wave detector in space with 3 spacecraft separated by millions of kilometers. It will detect low-frequency gravitational waves impossible to observe from Earth, including those from supermassive black hole mergers billions of years ago. By measuring how these ancient waves have stretched during their journey, LISA will trace cosmic expansion with unprecedented precision. But here's what makes LISA truly revolutionary. It might detect primordial gravitational waves from cosmic inflation itself. These ripples, frozen into space-time during the universe's first instant, could reveal whether dark energy and inflation are connected. If they share a common origin, we might finally understand why the universe began with rapid expansion and is ending with accelerating expansion, 2 phases of the same cosmic phenomenon separated by 14 billion years. The connection between dark energy and consciousness might sound like science fiction, but some physicists take it seriously. The quantum measurement problem, how observation causes quantum wave functions to collapse, might involve consciousness fundamentally. If consciousness plays a role in physics, and if the universe's information processing capacity relates to dark energy, then the accelerating expansion might be connected to the emergence of observers. The universe might be expanding faster because it's becoming more conscious, processing more information, creating more observers who collapse more wave functions. Recent observations of white dwarf supernovae have revealed something unexpected. These Type Ia supernovae, our standard candles for measuring cosmic distances, might not be as standard as we thought. The Zwicky Transient Facility has discovered that some explode differently depending on their environment. This doesn't invalidate dark energy's discovery, but it means our measurements might need refinement. The universe's acceleration might be slightly different than we calculated, potentially resolving the Hubble tension. Consider the role of magnetic fields in dark energy's story. Cosmic magnetic fields, stretching across millions of light years, affect how matter clumps and how cosmic rays propagate. The SOFIA Observatory, before its recent retirement, and ground-based radio telescopes have mapped these fields in unprecedented detail. Some theories suggest dark energy might interact with electromagnetic fields in ways we haven't detected yet. If true, the universe's magnetic skeleton might influence or be influenced by dark energy, creating feedback loops we're only beginning to imagine. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the world's largest radio telescope. By mapping billions of galaxies and tracking their motion over time, it will create a 3-dimensional movie of cosmic evolution. This will reveal not just where galaxies are, but how they're moving, their peculiar velocities that deviate from pure cosmic expansion. These deviations trace the gravitational pull of dark matter and the push of dark energy, revealing their cosmic dance in unprecedented detail. Let's explore the possibility that dark energy is an emergent phenomenon, not fundamental, but arising from something deeper. Just as temperature emerges from particle motion and isn't fundamental to individual atoms, dark energy might emerge from the collective behavior of quantum fields or space-time itself. Eric Verlinder's entropic gravity theory suggests gravity itself is emergent, arising from information and entropy. And if gravity is emergent, dark energy might be too, a statistical consequence of how information is distributed across the universe. The cosmic web's evolution under dark energy's influence is like watching a vast spider web in a growing wind. Initially, gravity pulled matter into filaments and nodes, creating the web structure. But as dark energy strengthens, it's like the wind picking up, stretching the web thinner, breaking connections. Computer simulations show that in the far future, the cosmic web will fragment completely. Each galaxy will become an island universe, isolated by vast voids that expand faster than light can cross them. Recent studies of galaxy clusters have revealed dark energy's subtle effects on the universe's largest gravitationally bound structures. The SPT-3G camera on the South Pole telescope can detect the tiny temperature changes in cosmic microwave background photons as they pass through clusters. This Sunyaev-Zeldovich effect lets us weigh clusters and see how their growth has slowed as dark energy became dominant. It's like watching the universe's construction project gradually shut down as the cosmic foreman, dark energy, calls workers off the job. The possibility of cyclic cosmology offers a radically different perspective on dark energy. In these models, the universe undergoes endless cycles of expansion and contraction. Dark energy drives expansion until the universe becomes empty and cold. Then quantum fluctuations trigger a new Big Bang. Each cycle might last trillions of years, with dark energy acting as the reset button that clears the stage for the next cosmic performance. We might be actors in an eternal play, with dark energy as the stage manager who brings down the curtain and raises it again. Time itself might be emergent from dark energy. Some theories suggest time isn't fundamental, but arises from change and entropy. Dark energy, by driving cosmic expansion and increasing the universe's entropy, might literally be creating time. The arrow of time, why we remember the past but not the future, could be a direct consequence of dark energy's push toward ever greater disorder. Without dark energy, time itself might not exist as we experience it. The discovery of dark energy has philosophical implications we're only beginning to grapple with. If most of the universe is invisible and incomprehensible to us, what does that say about our place in the cosmos? We're not just small, we're fundamentally disconnected from most of reality. It's as if we're fish in an aquarium, able to see our small world clearly but completely unaware of the vast ocean beyond the glass. Dark energy is that ocean, and we're just beginning to realize it exists. The most mind-bending aspect of dark energy might be its connection to the multiverse. If eternal inflation is correct, and many cosmologists believe it is, then our universe is just one bubble in an infinite foam of universes, each with potentially different values of dark energy. This isn't wild speculation, it emerges naturally from our best theories of cosmic inflation. The same mechanism that drove the universe's initial expansion might still be creating new universes right now beyond our cosmic horizon. Think about what this means. In some universes, dark energy might be stronger, tearing matter apart before stars can form. In others, it might be negative, causing rapid collapse. We exist in this particular bubble not by design, but by necessity. It's one of the rare universes where dark energy is weak enough to allow structure formation, but strong enough to be detected. The countless dead universes, devoid of observers, exist just as surely as ours, but with no one to witness their sterile perfection or violent chaos. Recent observations from the Dark Energy Survey have mapped dark matter around hundreds of galaxy clusters using weak gravitational lensing. This technique measures tiny distortions in background galaxy shapes caused by intervening mass. What they found challenges our expectations. Dark matter halos around clusters are less concentrated than predicted. This might mean dark energy affects dark matter in ways we haven't considered, perhaps through a fifth force that operates only on cosmic scales. The Axion, dark matter experiment and similar searches for dark matter particles have implications for dark energy too. If dark matter consists of ultralight particles like axions, they could form vast wave-like structures across the universe. These dark matter waves might interact with dark energy, creating regions where acceleration is stronger or weaker. We could be living in a cosmic ocean where dark matter waves and dark energy currents create complex patterns we're only beginning to detect. Let me share something that showcases how precisely we can now measure dark energy's effects. The Dark Energy Survey observed the same patch of sky repeatedly over 6 years, watching how galaxy clusters evolved. They found that clusters that should have grown by 50% grew by only 40%. This 10% discrepancy is dark energy's signature, the cosmic expansion that fights against gravity's attempt to build larger structures. It's like watching a construction project where an invisible force keeps stealing bricks from the walls. The cosmic neutrino background, those ghostly particles from the Big Bang's first second, affects dark energy measurements in subtle ways. These ancient neutrinos, which outnumber atoms by billions to one, have been streaming through space for nearly 14 billion years. As the universe expanded, they cooled and slowed, contributing a tiny but measurable amount to the universe's total energy density. Future experiments like Ptolemy might detect these relic neutrinos directly, providing a new window into dark energy's influence on the earliest universe. Here's a possibility that connects dark energy to black holes in an unexpected way. Some theories suggest that black holes aren't just endpoints of stellar evolution, but are connected to dark energy through quantum effects. As black holes evaporate through Hawking radiation over unimaginable timescales, they might inject energy into the vacuum itself. The universe's billions of black holes could collectively contribute to dark energy, linking the darkest objects in space to the force driving cosmic expansion. The cosmic dawn, when the first stars ignited about 100 million years after the Big Bang, might hold clues about dark energy's nature. The James Webb Space Telescope has detected galaxies from this era that are surprisingly massive and mature. If dark energy was different in the early universe, perhaps weaker or even attractive, it could explain how these structures formed so quickly. We might be seeing evidence that dark energy evolves, changing its character as the universe ages. Recent simulations using the world's most powerful supercomputers have revealed how dark energy affects galaxy formation on the smallest scales. The Eagle and illustrious TNG simulations model billions of particles over billions of years, tracking how dark matter, gas, and stars interact under dark energy's influence. They show that dark energy doesn't just affect large-scale structure, it subtly influences how galaxies form stars, merge with neighbors, and evolve over time. The possibility of dark energy stars represents one of the strangest ideas in modern astrophysics. These hypothetical objects would be powered not by nuclear fusion, but by dark energy itself. If dark energy can be concentrated or manipulated, advanced civilizations might harness it for energy. Some astronomers have even suggested looking for signs of dark energy manipulation as a form of technosignature, evidence of alien civilizations that have mastered the universe's dominant energy source. Let's examine how dark energy relates to the universe's information content. The holographic principle suggests that all information in a volume can be encoded on its boundary. As dark energy drives cosmic expansion, the boundary of our observable universe shrinks in terms of what we can access. We're losing information to dark energy, watching parts of the universe disappear beyond our cosmic horizon, never to be seen again. It's like a library where books gradually vanish, leaving us with ever fewer pages of the cosmic story. The Hubble tension, that discrepancy between different measurements of cosmic expansion, has become more puzzling with newer data. The HRS team, using Hubble Space Telescope observations of Cepheid variables and supernovae, consistently finds expansion about 9% faster than predicted from the cosmic microwave background. This might indicate that dark energy isn't constant but has changed strength over cosmic time. If confirmed, it would overturn the standard cosmological model and demand new physics. Time dilation caused by cosmic expansion means that we see distant events unfolding in slow motion. Supernovae in galaxies billions of light-years away appear to explode more slowly than nearby ones. This cosmic time stretching is direct evidence of dark energy's acceleration. The more distant the event, the more stretched it appears, like a cosmic movie playing at increasingly slow speeds the farther back we look. Dark energy isn't just expanding space, it's stretching time itself. The concept of phantom energy, where dark energy's density increases over time, leads to one of physics' most disturbing predictions. If dark energy is phantom energy with an equation of state parameter less than -1, the universe faces a catastrophic end. The Big Rip wouldn't just destroy structures, it would tear apart space-time itself. In the final instant, the expansion rate would become infinite, creating a singularity not of density but of emptiness. It's the opposite of the Big Bang, a moment when everything becomes nothing. Observations of the integrated Sachs-Wolf effect provide independent confirmation of dark energy. When cosmic microwave background photons pass through large-scale structures, they gain energy falling into gravitational wells and lose energy climbing out. But if dark energy causes those wells to shallow while photons traverse them, there's a net energy gain. The Dark Energy Survey has detected this effect by correlating galaxy positions with hotspots in the cosmic microwave background, providing another puzzle piece in the dark energy mystery. The connection between dark energy and quantum mechanics becomes even stranger when we consider vacuum fluctuations. According to quantum field theory, empty space is actually a roiling sea of virtual particles constantly appearing and disappearing. These quantum fluctuations should contribute enormous energy to the vacuum, so much that empty space should weigh more than all the matter in the universe combined. Yet dark energy's observed density is 120 orders of magnitude smaller than this prediction. This catastrophic disagreement suggests we're missing something fundamental about reality itself. Recent breakthroughs in understanding black hole information paradoxes might shed light on dark energy. The discovery that black holes have soft hair, subtle quantum information imprinted on their event horizons, suggests that information isn't destroyed but preserved in ways we're only beginning to understand. If the universe's event horizon, created by dark energy's acceleration, also stores information, then dark energy might be intimately connected to the universe's information processing capacity. We might be living inside a cosmic black hole turned inside out, with dark energy as the force maintaining the horizon. The Atacama Cosmology Telescope's latest measurements of the cosmic microwave background have revealed something unexpected. The universe might be slightly curved rather than perfectly flat. This tentative finding, if confirmed, would revolutionize our understanding of dark energy. A curved universe implies different total energy content, potentially explaining why dark energy has its observed value. It might mean we've been looking at the cosmic acceleration mystery from the wrong geometric perspective all along. Let me explain how dark energy affects the concept of cosmic simultaneity. In Einstein's relativity, there's no universal now. What counts as simultaneous depends on your motion and position in gravitational fields. Dark energy adds another layer of complexity. As it accelerates cosmic expansion, it creates an evolving definition of simultaneity on cosmic scales. Events that are simultaneous from one perspective might be separated by millions of years from another. Dark energy isn't just pushing galaxies apart, it's fragmenting our ability to define a coherent present moment across the universe. The discovery of peculiar velocities, galaxies moving differently than pure cosmic expansion predicts, reveals dark energy's subtle influence on cosmic flows. The Great Attractor, a gravitational anomaly pulling galaxies in our local region, competes with dark energy's push. By mapping these cosmic currents, surveys like the Cosmic Flows project trace the tug-of-war between gravity's pull and dark energy's push. It's like watching rivers flow uphill, defying gravity through an invisible force that grows stronger with distance. String theory's landscape problem directly connects to dark energy. The theory predicts 10 to the 500th power possible universes, each with different physical laws and constants. Dark energy's value varies across this vast landscape of possibilities. We might exist in our particular valley of this cosmic landscape simply because it's one of the few where dark energy allows stars, planets, and life. The multiverse isn't just possible, it might be necessary to explain why dark energy has exactly the value we observe. Recent studies of gamma-ray bursts, the universe's most powerful explosions, provide unique tests of dark energy. These cosmic flashbulbs, visible across billions of light-years, serve as standardizable candles, similar to supernovae but observable at even greater distances. The Swift and Fermi space telescopes have catalogued hundreds of these events, revealing that the universe's expansion history matches dark energy predictions even in the cosmic dawn. These ancient explosions confirm that dark energy has been shaping the universe for most of its history. The possibility that dark energy could decay changes everything about the universe's future. If dark energy is a scalar field slowly rolling down a potential energy hill, it might eventually reach a minimum and stop driving acceleration. The universe would transition from accelerating expansion to coasting or even contraction. This quintessence scenario means the current era of acceleration might be temporary, a cosmic phase, rather than an eternal condition. Future civilizations might witness a universe utterly different from ours. Let's explore how dark energy affects the Fermi paradox, the puzzle of why we see no signs of alien civilizations. Dark energy limits the ultimate size of any cosmic civilization. As acceleration continues, galaxies become isolated islands impossible to travel between. Any civilization, no matter how advanced, will eventually be trapped in its local group of galaxies. Dark energy might be the universe's way of enforcing cosmic solitude, preventing any species from dominating more than a tiny fraction of space. The relationship between dark energy and modified gravity theories has taken an unexpected turn. New observations of gravitational waves traveling through galaxy clusters show that gravity behaves exactly as Einstein predicted, even on large scales where some theories predict deviations. This strengthens the case that dark energy is real rather than a misunderstanding of gravity. Yet modified gravity theories keep evolving, finding new ways to mimic dark energy's effects while predicting subtle differences that future experiments might detect. Quantum entanglement experiments have revealed that information can be shared instantly between particles regardless of distance. Some physicists wonder if dark energy might involve similar quantum correlations on cosmic scales. Perhaps distant regions of space are quantumly entangled, and dark energy represents the tension in these cosmic-scale quantum connections. As the universe expands, these quantum correlations stretch, potentially driving acceleration through mechanisms that blur the boundary between quantum mechanics and cosmology. The cosmic microwave background's tiny temperature fluctuations encode information about dark energy in subtle ways. The peaks and valleys in the CMB's power spectrum how much variation exists at different angular scales, depend on the universe's composition, including dark energy. The Simons Observatory, currently being built in Chile's Atacama Desert, will measure these fluctuations with unprecedented precision, potentially detecting signatures of early dark energy that influenced the universe's first moments. Recent observations suggest that dark energy might clump slightly around massive structures. While we think of dark energy as perfectly smooth, some theories predict it could have tiny density variations. The Dark Energy Survey found hints that cosmic voids, vast empty regions between galaxy clusters, might have slightly different dark energy density than average. If confirmed, this would mean dark energy isn't just a uniform background but has texture, structure, perhaps even dynamics we haven't imagined. The role of dark energy in cosmic inflation remains one of physics' deepest mysteries. Inflation required a temporary form of dark energy that drove exponential expansion, then decayed into matter and radiation. But what if inflation never completely ended? Eternal inflation theory suggests that inflation continues in some regions while ending in others, creating pocket universes like ours. Dark energy might be inflation's dying ember, the last trace of the force that created everything we see. The technological implications of understanding dark energy could transform civilization. If we could harness or manipulate dark energy even slightly, it would provide unlimited power. A dark energy engine could accelerate spacecraft without fuel, create warp drives that compress space ahead and expand it behind, or generate energy from empty space itself. While this sounds like pure science fiction, remember that nuclear energy seemed equally impossible before we understood atomic physics. Dark energy represents 70% of the universe's energy budget. Learning to tap even a fraction would revolutionize everything. Recent discoveries about how galaxies die reveal dark energy's role in cosmic evolution. The ALMA telescope has observed galaxies suddenly stopping star formation, becoming red and dead ellipticals. This process, called quenching, happens when galaxies can no longer accrete fresh gas from their surroundings. Dark energy accelerates this cosmic starvation by pulling gas clouds apart faster than gravity can gather them. We're witnessing dark energy slowly strangling the universe's ability to create new stars, new planets, new possibilities for life. The boundary between quantum mechanics and general relativity blurs when we consider dark energy at the smallest scales. The Planck length, roughly 10 to the minus 35 meters, represents the scale where quantum gravity effects should dominate. But dark energy operates on scales of billions of light years. This vast separation of scales, 60 orders of magnitude, might be telling us something profound. Perhaps dark energy is the macroscopic manifestation of quantum gravity, the universe-scale footprint of physics at the smallest possible scale. Let me share something that demonstrates just how precisely balanced our universe is. If dark energy were stronger by a factor of 10, galaxies would never have formed. If it were weaker by a similar factor, the universe would have recollapsed already. We exist in an incredibly narrow window where dark energy is strong enough to be detected, but weak enough to allow cosmic structure. This fine-tuning is so extreme that it demands explanation. Either we're incredibly lucky, we're in a multiverse where different regions have different values, or there's a deeper principle we haven't discovered yet. The cosmological lithium problem might be connected to dark energy in unexpected ways. Big Bang nucleosynthesis predicts how much hydrogen, helium, and lithium formed in the universe's first minutes. Observations match predictions perfectly for hydrogen and helium, but we see only 1/3 the expected lithium. Some physicists suggest early dark energy, a temporary boost to expansion in the universe's first moments, could explain this discrepancy. If dark energy varied in the early universe, it would change nuclear reaction rates, potentially solving this decades-old puzzle. Recent studies of ultra-diffuse galaxies, ghostly galaxies with few stars spread over vast areas, reveal structures that shouldn't exist according to standard models. These galaxies have survived despite dark energy's disrupting influence, held together by dark matter halos far more massive than expected. They're like cosmic fossils, preserving information about how galaxies formed when dark energy was weaker. The Dragonfly telephoto array has discovered hundreds of these phantom galaxies, each one a challenge to our understanding of structure formation. The interplay between dark energy and cosmic magnetic fields creates phenomena we're only beginning to understand. Radio observations reveal magnetic fields stretching across millions of light-years, threading through the cosmic web like invisible cables. These fields affect how cosmic rays propagate, how gas collapses to form stars, and possibly how dark energy manifests on different scales. The LOFAR radio telescope array has mapped these cosmic magnetic fields in unprecedented detail, revealing a hidden skeleton that might influence or be influenced by dark energy. Here's a mind-bending possibility. Dark energy might be evidence that our universe is a simulation. If reality is computed, there must be finite computational resources. Dark energy could represent the computational cost of expanding space. As the universe grows, more processing power is needed to simulate each region. The acceleration might reflect the simulation allocating resources, spreading computational density thinner as space expands. It's a wild idea, but it makes testable predictions about how dark energy should behave at different scales. The discovery of supervoids, vast cosmic deserts nearly empty of galaxies, provides natural laboratories for studying dark energy. The Eridanus supervoid, spanning nearly 1 billion light-years, creates a cold spot in the cosmic microwave background as photons lose energy crossing this cosmic desert. These voids are dominated by dark energy, with matter's influence nearly absent. By studying how voids evolve and affect surrounding structures, we can isolate dark energy's effects from gravity's complications. Quantum experiments with Bose-Einstein condensates might reveal connections between dark energy and quantum mechanics. These ultra-cold atomic clouds exhibit quantum behavior on macroscopic scales, creating laboratory universes where scientists can simulate cosmic phenomena. Recent experiments have created acoustic black holes and tested theories of emergent gravity. Future experiments might simulate dark energy, testing whether it emerges from quantum entanglement or information theory in ways we can manipulate and measure. The cosmic web's filamentary structure encodes the history of dark energy's influence. Galaxy surveys reveal that filaments connecting galaxy clusters are stretching and thinning over time, eventually snapping as dark energy overcomes gravity's binding force. Computer simulations predict that in about 100 billion years, all cosmic filaments will have broken, leaving every galaxy cluster isolated in its own island universe. We're living in the cosmic web's golden age before dark energy tears it completely apart. Recent observations of Type Ia supernovae with the Hubble Space Telescope have revealed unexpected diversity in these standard candles. Some supernovae appear to be influenced by their host galaxy's properties in ways that affect their brightness. This doesn't invalidate dark energy's discovery, but it means our measurements need refinement. The Vera Rubin Observatory will observe millions of supernovae, providing statistics to account for this diversity and measure dark energy with even greater precision. The possibility of early dark energy, a brief period when dark energy was stronger just after the Big Bang, could solve multiple cosmological puzzles. This early boost to expansion would affect how sound waves propagated through the primordial plasma, changing the cosmic microwave background's patterns. It might also explain why the universe appears older than some of its oldest stars, a paradox that has troubled astronomers for years. The CMB-S4 experiment will search for signatures of early dark energy with unprecedented sensitivity. Let's consider dark energy's role in the ultimate question: is the universe infinite or finite? If space is positively curved even slightly, the universe is finite but unbounded, like the surface of a sphere but in 3 dimensions. Dark energy would eventually cause such a universe to expand beyond the point where light could circumnavigate it, effectively making it infinite from any observer's perspective. We might live in a universe that transforms from finite to effectively infinite through dark energy's acceleration. The most recent data from pulsar timing arrays has opened an entirely new window into dark energy's nature. These networks of millisecond pulsars, spinning hundreds of times per second with clockwork precision, act as galaxy-sized gravitational wave detectors. Nanograv and the European Pulsar Timing Array have detected a background hum of gravitational waves permeating the universe. This cosmic gravitational wave background might carry information about dark energy's influence on supermassive black hole mergers throughout cosmic history. Consider what happens at the edge of our observable universe. The cosmic horizon, currently about 46 billion light-years away, marks the boundary of what we can ever observe. Dark energy is shrinking this horizon in a peculiar way, not in absolute distance, but in terms of what we can interact with. Galaxies crossing this horizon don't disappear instantly. Their light redshifts toward infinity, freezing them in time from our perspective. We watch them fade to black, their final photons stretched beyond detection, lost to dark energy's inexorable expansion. The discovery of ultra-high energy particles, called "oh my god" particles, presents a dark energy puzzle. These cosmic rays have energies that shouldn't be possible. They should interact with cosmic microwave background photons and lose energy before reaching Earth. Yet we detect them. Some theories suggest dark energy might create shortcuts through space or modify how particles propagate at extreme energies. The Pierre Auger Observatory and Telescope Array are mapping these impossible particles, potentially revealing dark energy's influence on the universe's most energetic phenomena. Recent breakthroughs in laboratory cosmology are bringing dark energy studies down to Earth. Scientists have created analog models of cosmic expansion using ultra-cold atoms, flowing water, and even sound waves. These tabletop universes can't replicate dark energy directly, but they can test mathematical frameworks and reveal unexpected behaviors. The University of Nottingham created a sonic black hole that demonstrates how horizons form, providing insights that might apply to dark energy's cosmic horizon. The relationship between dark energy and time crystals reveals deep connections we're only beginning to explore. Time crystals are structures that repeat in time rather than space, maintaining perpetual motion without energy input. They exist because of subtle balances between quantum mechanics and thermodynamics. Some theorists suggest dark energy might be a cosmic-scale time crystal, a temporal structure that drives perpetual expansion without depleting. The universe's acceleration might be the largest time crystal possible. Let me tell you about the Dark Energy Survey's most surprising discovery, cosmic shear. By measuring how dark matter's gravity distorts the shapes of billions of galaxies, scientists have mapped the invisible scaffolding that holds the universe together. This weak gravitational lensing reveals that matter is distributed more smoothly than expected. Dark energy seems to have prevented matter from clumping as much as models predict. It's like dark energy has been gently stirring the cosmic pot, keeping ingredients from settling. The possibility of negative mass, while seemingly absurd, could explain dark energy naturally. In general relativity, negative mass would gravitationally repel normal matter while being attracted to it, creating a cosmic chase that accelerates both. If the universe contains trace amounts of negative mass particles created in the Big Bang, their cumulative effect might manifest as dark energy. Experiments at Alpha at CERN are testing whether antimatter falls up or down, potentially revealing whether negative mass exists. Observations of the Lyman alpha forest, absorption lines in quasar spectra from intergalactic hydrogen, trace cosmic structure evolution with extraordinary precision. Each absorption line represents a hydrogen cloud between us and the quasar. The pattern of these lines reveals how matter clumped over billions of years, showing dark energy's gradual dominance. The DESI survey is measuring millions of these cosmic barcodes, creating a three-dimensional map of how dark energy has shaped structure formation throughout cosmic history. The cosmic confusion between dark matter and dark energy might hide a deeper unity. Both are dark because they don't interact electromagnetically. Both dominate the universe's mass-energy budget. Some theories propose they're different aspects of a single phenomenon, perhaps a fluid that exhibits different properties at different densities or temperatures. In dense regions, it acts like dark matter, providing extra gravity. In empty regions, it acts like dark energy, driving expansion. This dark fluid model could simplify our cosmic inventory from 3 components to 2. Recent studies of cosmic dawn with the James Webb Space Telescope have revealed that early galaxies assembled differently than expected. They formed stars more efficiently, grew supermassive black holes faster, and enriched their gas with heavy elements sooner than models predict. This might indicate that dark energy was different in the early universe, perhaps oscillating or evolving rapidly before settling to its current value. We might be seeing fossils of dark energy's cosmic adolescence. The thermodynamics of dark energy presents profound puzzles. Normally, when space expands, it cools, like gas expanding from a compressed cylinder. But dark energy maintains constant density as space expands, seeming to violate conservation of energy. Where does this new energy come from? One answer involves the universe's gravitational field. As space expands, gravitational potential energy becomes increasingly negative, exactly balancing dark energy's positive contribution. The universe's total energy might be exactly 0. Quantum tunneling could connect dark energy to the universe's ultimate fate. If dark energy represents a metastable vacuum state, quantum fluctuations could eventually trigger a transition to a lower energy state. This wouldn't happen gradually. It would start at a point and expand at light speed, rewriting physics as it spreads. The probability is incredibly small, but given infinite time, it becomes inevitable. Dark energy might be a cosmic time bomb with a fuse billions of years long. The holographic principle suggests our 3-dimensional universe might be encoded on a 2-dimensional surface, like a hologram. Dark energy plays a crucial role in this encoding. As the universe expands, the encoding surface grows, allowing more information. But dark energy also creates a cosmic horizon that limits accessible information. This tension between growing capacity and shrinking accessibility might be fundamental to reality's structure. We might live in a cosmic hologram where dark energy controls the projection. Recent advances in gravitational wave astronomy have revealed that dark energy affects how black holes merge. LIGO and Virgo have detected black hole collisions from when the universe was younger and dark energy was weaker. The merger rate and black hole masses from different cosmic epochs trace dark energy's growing influence. Future detectors like the Einstein telescope will observe millions of mergers, creating a gravitational wave map of dark energy's cosmic evolution. The possibility that consciousness plays a role in dark energy sounds mystical, but has serious proponents. The quantum Zeno effect shows that observation can freeze quantum systems. If consciousness causes wave function collapse, and if the universe's wave function relates to dark energy, then the emergence of observers might have triggered cosmic acceleration. The universe might be expanding faster because it's being observed. It's a radical idea that blurs the boundary between physics and philosophy. As we stand at the threshold of understanding dark energy, we face a humbling truth. We are the universe trying to understand itself. Every observation, every theory, every late night spent puzzling over data is the cosmos examining its own nature through conscious beings made of stardust. Dark energy isn't just a scientific puzzle, it's a mirror reflecting our deepest questions about existence, purpose, and fate. The next generation of dark energy experiments will revolutionize our understanding. The Nancy Grace Roman Space Telescope will observe billions of galaxies, tracking cosmic expansion with precision that makes current measurements look crude. The Square Kilometre Array will map cosmic structure using radio waves from hydrogen gas spanning most of the universe's history. The Extremely Large Telescope will directly observe the universe's expansion in real time, watching distant objects accelerate away over decades. We're building cosmic eyes that will see dark energy's fingerprints everywhere. But here's what keeps me awake at night. What if dark energy is trying to tell us something profound about the nature of existence itself? Every great revolution in physics has revealed that reality is stranger than we imagined. Quantum mechanics showed us that certainty is an illusion. Relativity revealed that space and time are fluid. Dark energy might be pointing toward an even deeper truth, that the universe isn't just expanding, but evolving, perhaps even thinking. Consider the cosmic coincidence that we exist precisely when dark energy becomes noticeable. Earlier, matter's gravity dominated completely. Later, dark energy will rule absolutely. We live in the brief cosmic moment when both matter and dark energy have comparable influence. This isn't just luck, it might be necessity. Perhaps consciousness can only emerge during this delicate balance, when the universe is neither collapsing nor expanding too fast for complexity to develop. The discovery of dark energy echoes through every scale of existence. It affects how atoms might behave in the far future, how stars form and die, how galaxies dance through space, and how the universe itself will end. It connects quantum mechanics to cosmology, links the smallest scales to the largest, and bridges the gap between abstract mathematics and observable reality. Dark energy isn't just one piece of the cosmic puzzle, it's the table the puzzle sits on. Recent philosophical work on the participatory universe suggests that observers aren't passive witnesses but active participants in cosmic evolution. John Wheeler proposed that the universe requires observers to actualize its existence. No observers, no universe. If consciousness plays a fundamental role in physics, dark energy might be the universe's response to being observed. The acceleration might have begun when the first conscious beings emerged somewhere in the cosmos, whenever and wherever that was. The implications for humanity's future are staggering. If we survive long enough, we'll witness the universe's transformation under dark energy's influence. In 1 trillion years, all galaxies beyond our local group will disappear beyond the cosmic horizon. Future astronomers will see only our merged galaxy floating in absolute darkness. They'll have no evidence of the Big Bang, no cosmic microwave background to observe, no distant galaxies to study. Unless we preserve our current knowledge, they might conclude they live in a static, eternal universe, ironically, returning to pre-20th century cosmology. But knowledge preservation becomes meaningless if we're alone. The search for extraterrestrial intelligence takes on new urgency in a dark, energy-dominated universe. If civilizations are rare, dark energy ensures they'll become isolated forever. The window for contact between distant civilizations is closing. In the far future, even if intelligent life is common, each civilization will be alone, separated by voids that expand faster than light. Dark energy might be the universe's way of enforcing ultimate solitude. The relationship between information and dark energy suggests a cosmic computational framework. If the universe processes information, dark energy might represent computational overhead, the cost of running reality's operating system. As the universe evolves and complexity increases, more computational resources are needed. The acceleration might reflect the universe allocating processing power, expanding to accommodate growing information content. We might live inside a cosmic computer that's upgrading its hardware through expansion. Recent attempts to unify dark energy with modified gravity have produced the dark gravity framework. Instead of separate dark matter and dark energy, perhaps gravity itself behaves differently than Einstein predicted. On solar system scales, Einstein's theory works perfectly. But on cosmic scales, gravity might become repulsive, creating the illusion of dark energy. The Laser Interferometer Space Antenna will test this by detecting gravitational waves from across the universe, revealing whether gravity itself drives cosmic acceleration. The deepest question remains, is dark energy fundamental or emergent? Fundamental properties can't be explained by anything deeper, they simply are. Emergent properties arise from underlying processes like temperature emerging from molecular motion. If dark energy is fundamental, we must accept it as a brute fact about reality. If it's emergent, discovering what it emerges from would revolutionize physics more profoundly than any discovery since quantum mechanics. As I contemplate dark energy's mystery, I'm struck by how it embodies the human condition. We're finite beings trying to understand the infinite, temporary arrangements of matter, contemplating eternal forces, small creatures grappling with the larger structures in existence. Dark energy reminds us that the universe is far stranger, far grander, and far more mysterious than our ancestors imagined. Yet we persist in trying to understand, driven by the same curiosity that led our species to look up at the stars and wonder. The discovery that our universe is accelerating ranks among humanity's greatest intellectual achievements. In just over 2 decades, we've gone from complete ignorance of dark energy to mapping its effects across billions of years and billions of light years. We've built instruments sensitive enough to detect space-time ripples smaller than atomic nuclei and telescopes that see to the edge of the observable universe. We've turned dark energy from an impossibility into astronomy's central mystery. But perhaps dark energy's greatest gift isn't scientific knowledge, it's perspective. Knowing that we're made of stardust living in a universe dominated by invisible forces should fill us with awe and humility. We're participants in a cosmic drama whose script we're still learning to read. Every atom in our bodies, every thought in our minds, every emotion in our hearts exists because the universe's fundamental forces are precisely balanced. Dark energy is part of that balance, the cosmic counterweight that prevents gravity from collapsing everything into a singular point. As you go about your daily life, remember that you're surrounded by dark energy. It fills the space between atoms, between planets, between galaxies. It's pushing the universe apart, even as gravity pulls you toward Earth. You exist at the intersection of these cosmic forces, a conscious arrangement of matter capable of contemplating the very forces that created you. That's not just remarkable, it's miraculous. The universe's accelerating expansion means we live in a privileged time. We can see galaxies that future observers never will. We can study the cosmic microwave background before it fades beyond detection. We can trace the universe's history from the Big Bang to the present and project its future toward infinity. We are the universe's memory, preserving knowledge of its youth before dark energy erases the evidence. So look up at the night sky with new eyes. Those points of light aren't just distant suns, they're beacons in an accelerating universe, racing away from us faster each moment. The darkness between them isn't empty, but filled with the most abundant force in existence, and you, looking up, are the universe becoming aware of itself, marveling at its own mystery, reaching toward understanding that may forever elude us, but makes the journey worthwhile. Dark energy reminds us that the greatest discoveries often begin with admitting ignorance. We don't know what dark energy is. We don't know why it has the strength it does. We don't know if it's constant or evolving. But from this foundation of uncertainty, we build towers of knowledge, each observation adding another brick, each theory another flaw. Someday, perhaps soon, someone will place the keystone that completes our understanding. Until then, we continue the most human of endeavors, asking questions of the cosmos and listening carefully for its whispered answers. The universe is accelerating and we are along for the ride. What a time to be alive, what a mystery to contemplate, what a future to face, knowing that the cosmos itself is our laboratory, our teacher, and our home. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. If nothing exists outside the universe, what is it expanding into? Discover why the universe isn't expanding into empty space, how space itself is stretching, and what modern physics, general relativity, and the Big Bang Theory reveal about the boundaries of existence. See you there.